I hope everybody is fine. And in this video, I'll be talking about uncertainty principle. In fact, there are a long range of routes that can be utilized uh, to to reach out to uncertainty principle. And we all understand that this principle simply states that the uncertainty in the measurement of position, the product of the uncertainty in the measurement of position and the uncertainty in the measurement of momentum is greater or equal to h bar by 2, where this delta x is a representative of the uncertainty in the measurement of the position of the particle, and delta p is the uncertainty in the measurement of the momentum of the particle. Now, if we start with the wave function, and if we start with the wave function of a wave packet, wave function of of a wave packet, and and this wave packet is basically it's the superposition. It's the superposition of a long range of waves. And this superposition, let's assume that there is a superposition between the waves, and this superposition leads to a wave packet. And we can think of a wave packet like this. And we can mathematically translate this superposition of the waves. This superposition of waves can be translated in terms of Fourier transform. And if we have to write down the wave function for this wave packet, we can write down it. Let's assume that psi is the wave function. It's a function of say position and time, and and this wave function is 1 by under root of 2 pi integral minus infinity to infinity and phi of k e to the power of I kx minus omega t dk. So what we have here is we have the Fourier transform. That's a representative of the wave function of this wave packet. So what we have a wave packet, and this phi of k is the representative of the amplitude. It is the amplitude of the wave packet. Sorry. Now, if we write down this wave function at time t equals 0, so we can write down psi of x is 1 by under root of 2 pi integral minus infinity to infinity, then phi of k e to the power of I kx dk. So this will be the wave function for this wave packet that we have been talking about, that's linked to the particle, a microscopic particle. And this will be the wave function. And we can imagine this this wave function, and at the same time we can use inverse Fourier transform for this equation. If I write the inverse Fourier transform of this equation, what will I obtain? I will obtain phi of k equals 1 by under root of 2 pi integral minus infinity to infinity. Then I'll have psi of x e to the power of minus iota kx and dk. Yeah. So we have two equations. Let me write down. So I have wave function in terms of k space. And obviously this k spaces has a link with the momentum of the particle. And I have the wave function 1 by under root 2 pi integral minus infinity to infinity phi of k e to the power of I to kx dk. Now this is my wave function in the position space. In the position space. Now, if I have to think of this position this position wave function, we can show it like this, a wave packet having, okay, this will be my psi of x. So it will go like this, and then it will go like this. And we can see here that the magnitude of this wave function is maximum at x equal to 0. So if I define this range of this wave packet from x1 to x2, so I will have the change in the position. The change in the position can be written as delta x. Now, if I plot in the similar way for the case space, in the case space, what I will obtain, so this is my position space, this is my x space, and this is my k space. Now, if I draw this this k space, it will have the same kind of nature, and it will have a maxima. So this is over phi of k now in this case, and there is a range over which this phi of k is defined, and obviously the value of this phi of k is maximum at k equal to some k naught, and the width of this range of k space is delta k. And what we have here is we have two terms. One is delta x and another is delta k. And we have a relation between this delta k and delta x. And what's that relation? That is, the product of this delta x and delta k is greater or equal to 1. Now, if this is the case, we can think of writing delta x as greater or equal to 1 by delta k. So if there is the large change in the momentum space, if there is a large change in the momentum space, the change in the position space is going to be minimal. So this delta x will be small at the time this delta k is large. I mean, if both the things are taken simultaneously, then this delta k being large is indicative of the fact that this delta x is small, and vice versa. So there is, if the uncertainty in the measurement of the k space, which is basically the momentum space, is large, then the uncertainty in the measurement of the position of the particle is small, and the reverse is true. And at the same time, we can, as we can think of writing this momentum, and momentum is h cross k. Okay, so this delta p can be written as h cross delta k. So I can use for delta k here as delta p by h cross. So this delta x is greater or equal to 1 by delta p by h cross. So this is delta k, yeah, and this is delta p. So for delta k, I have this. So this h will go up, and we will have delta p delta x is greater or equal to h cross. And this is how we realize we realize the validity of Heisenberg's uncertainty principle using the concept of wave packet, using the concept of superposition, and translating the superposition in terms of the Fourier transform, and writing down the Fourier transform in the position space, and then writing its inverse Fourier transform in terms of the k space, and using the relation between delta k and delta x leads to the well-known uncertainty principle.